Well, dear students, now all of you are equipped with that how to prepare a half cell, right? So see what is the cause of this electrode potential and how this electrode potential develops, right? See, suppose that if you have taken a zinc rod in a zinc sulfate solution. Suppose that you have taken a zinc rod in a zinc sulfate solution, right? Suppose that inert container is this, and you have zinc rod, like this, right? So this is a zinc rod, and zinc sulfate electrolyte we have taken here. Zn2 plus SO4 minus minus, right? Suppose that this is assembly is given. So what is happening here? See, after some time, see, zinc sulfate is electrically neutral. This solution is electrically neutral. Zinc rod is electrically neutral. But what is happening here? After some time, what we observe that zinc rod is negatively charged. Zinc rod is negatively charged with respect to the solution. See, zinc rod is negatively charged and solution is positively charged. See, this solution is positively charged. Means what is happening here? Here polarization takes place, right? So zinc rod is negatively charged and solution is positively charged. Okay. Now see what mechanism here used to develop this charge. This is a spontaneous phenomenon. This is a natural phenomenon. So when zinc rod, we can write here, when when zinc rod is merged with zinc sulfate ZnSO4 or electrolyte with reversible ion, electrolyte with reversible ion Zn2 plus aqueous, Zn2 plus aqueous, right? The rod is zinc rod is negatively charged, zinc rod negatively charged, and solution positively charged. Positively charged. right? See what is happening here. So for this, we have to see what is the, inside this zinc, because we know what is inside this zinc sulfate, Zn2 plus and sulfate ions are there, and water molecules are there, some H plus and some OH minus are there in this solution, right? And all of you are knowing that the whole system is always be electrically neutral, right? Whole system is always electrically neutral, but local polarization is developed in the vicinity of this zinc rod. So if we see here, if we try to visualize inside the zinc rod, what we can see, that see this Zn lattice of this zinc metal, Zn2 plus are there, Zn2 plus are there in the zinc rod, and the relative position of Zn2 plus is fixed, Zn2 plus, Zn2 plus, and these electrons to electron, they are freely moving inside the zinc lattice. But remember, these electrons are not automatically or spontaneously released from the surface. They are still in the force of attraction with the zinc ions. So this is called metallic bonding. All of you must be aware. So these are the electrons and Zn2 plus ions. So what is happening when this zinc rod is placed with zinc sulfate? So there must be some oxidation reduction process is going on. See, the zinc solid means zinc rod, zinc ions which are present are zinc ions which are present at the rod. This lattice will break when this will put into the zinc sulfate, and this lattice will cleave, and some of zinc ions will transfer to the solution. Zn2 plus, some of zinc ions are coming to the solution plus 2 electron and gets hydrated, aqueous. So the question arises here that from where this energy is managed. This is a spontaneous process, so definitely energy is managed by system itself through hydration or through some other phenomena. The energy is managed by its system only. There is no need to you supply the energy from outside. But I cannot say that without energy this process is happening. Energy must be involved there, but that energy is managed by system itself, right? See, two opposite processes are set up here. Zinc ions are oxidized. See, this is oxidized to Zn2 plus. This zinc ion is oxidized here. This is oxidized. And this Zn2 plus to zinc, this is reduced. Reduction. So we can say that oxidation and reduction process are set up. Oxidation and reduction process are set up in this reaction, in this system. Okay, but see, as all of you are knowing in the reversible reaction, that this is the forward reaction and this is the backward reaction. So initially the rate of forward reaction is what? More, and rate of backward reaction is less. Means rate of forward and rate of backward reaction means the extent of oxidation and extent of reduction is different initially. But after some time this system will come into the at the equilibrium. And all of you are knowing equilibrium not means the balanced, means reactant and products are equal. This is also equilibrium, this is also equilibrium. Means at equilibrium, equilibrium is not recognized as the quantity of reactant is equal to the quantity of product. May or may not. Means equilibrium may be shifted in one direction. So basically when this zinc rod is placed in a zinc sulfate solution, a spontaneous oxidation reduction reaction starts. Initially the rate of oxidation and rate of reduction is different. After some time equilibrium is established, and at equilibrium the equilibrium is shifted in the forward direction. So I am making this arrow large, right? So large arrow always represents the shifting of equilibrium. So this equilibrium is shifted in the forward direction, right? Now it is clear. So this is a dynamic process. So equilibrium is shifted on the right hand side. So more and more zinc ions will come. See, more and more zinc ions, these zinc ions were coming into the solution. Compared, and less number of zinc ions going to the rod, result of which electrons are left at the rod and Zn2 plus are excess in the solution. And this zinc 2 plus, so the excess of Zn2 plus means if you have taken this 1 molar, so after at equilibrium the concentration of zinc ion in the solution that will be more than 1 molar. If you have taken this ZnSO4 1 molar, if you have taken ZnSO4 1 molar at T is equal to 0, so I should write here separately. So when zinc rod is merged with ZnSO4 solution or electrolyte with reversible ion like Zn2 plus, Zn rod is negatively charged and solution is positively charged, and this is the result of, as a result of spontaneous oxidation dominating reduction reaction, right? As a result of spontaneous oxidation and reduction reaction, right? And I am giving you some quantitative support for this. And Zn2 plus ion concentration is 1 molar at T is equal to 0, then T is equal to 0 means in the beginning of the process, but at equilibrium the concentration of Zn2 plus ion in solution is more than 1 molar. Means what is happening here? Zn2 plus ions, more and more Zn2 plus ions are diffused into the solution compared to the Zn2 plus ion from solution to deposit over the rod. Now it is clear. Means as a result of this formation of this electrical double layer, there is a change in concentration in the solution as well. Clear? So hopefully all of you are clear this story, that any metal rod if immersed in a electrolytic solution, the rod is either negatively charged or positively charged depending on the nature of that metal with respect to the solution. And why this charge is developed? This is due to the spontaneous setup of oxidation reduction reaction. And definitely one process will dominate for the given electrode, right? Now come to the physics. See, this electrical double layer, the magnet, now equilibrium established, means the number of negative charge and positive charge are fixed. So what will happen? The electrical double layer is formed here. So the magnitude of potential difference between rod and solution, the magnitude of potential difference, see, the magnitude of potential difference between rod and solution is called electrode potential. Very simple. So electrode potential is the magnitude of potential difference between rod and solution metal rod and solution having reversible ion ion is called electrode potential. Right? And electrode potential is represented by a symbol E. Right? So hopefully all of you are clear what is electrode potential. So electrode potential is defined as the magnitude of potential difference between rod and solution when a metal rod is immersed in a solution having reversible ion. Right? See, now the next question arises, this magnitude of electrode potential depends on what factors? So the magnitude of electrode potential potential depends on the following factors. So number one, the nature of electrode or nature of matter, nature of electrode. Right? Means you have taken zinc, copper, silver, hydrogen, chlorine, whatever electrode you have taken, that nature of that matter, or you can say nature of matter. Second factor concentration of electrolyte. electrolyte, and more precisely the concentration of reversible ion. Concentration of reversible ion, right? Or ion which affects the concentration of reversible ion. In complex cells, it may be some apparent ion is there. So concentration of electrolyte or concentration of reversible ion, it's okay. Third factor is temperature. Temperature of experiment. Temperature of experiment. And fourth factor is the pressure of experiment. And here one more point I would like to add. Concentration of electrolyte in case of reversible ion and pressure of gas right, for gaseous electrode, for gaseous electrode, right? So concentration of electrolyte means reversible ion and pressure of, or not or, right? And or you can add here, because when there is no gaseous, so then it will not depend. Okay, but for gaseous electrode you have to consider pressure also. So these are the factors on which electrode potential, magnitude of this potential difference is depends. Okay. See, if we change for nature of electrode, it is always constant for the given electrode. If we control this concentration and pressure of gas, temperature of experiment and pressure of experiment, so we can specify the value of electrode potential, and this is called standard electrode potential. So if we take pressure of experiment, P of experiment is 1 bar temperature of the experiment, T for the experiment constant, and concentration of reversible ion, not electrolyte, concentration of reversible ion is 1 molar, and partial pressure of the gas, if gaseous electrode, is 1 bar, right? So under this condition, the magnitude of potential difference between rod and solution is called standard electrode potential. So magnitude of potential difference, under above condition is called standard electrode potential. Standard electrode potential. Right? It is represented by E naught. Right? So this is called standard electrode potential. Right? See here. Again, you have to be very careful. Pressure of the experiment means the environment of pressure means under laboratory condition, whatsoever the pressure you have taken, that should be 1 bar. Temperature is constant. See, again focus here. Temperature should be constant. And remember, you can choose any temperature of your own choice. And you know, dear students, be careful here. Many times, people are doing mistake here that they were writing temperature should be 298 Kelvin. But not, this is not like that. Temperature could be anything. It is of your interest. You can set your interest temperature, but it should be constant. See, for defining any standard function, temperature is not necessarily 298 Kelvin. Remember and listen carefully. For expressing any standard thermodynamic function, temperature is not necessarily 298 Kelvin. Temperature should be constant. It could be 298 Kelvin, it could be 300 Kelvin, it could be 500 Kelvin. You can choose yourself. The only requirement is pressure should be constant and 1 bar. For every standard thermodynamic function, whether it's delta G, delta H, delta S, or here E naught. So you can say that it means for any given electrode, we may have 2 different values of E naught. The answer is yes. We may have 2 different values of E naught. Don't say that only one value is only exists for E naught. E naught may have different value at different temperature. But every value is said to be standard electrode potential if pressure is 1 bar and this all other features are same here. Because see, in every case I have written 1, 1, 1. But here I have not written 298 Kelvin. I have written constant. This should be constant. Okay. Now clear? So for any given electrode, standard electrode potential may be 2 or 3 different, may have 2 or 3 different values, but definitely at different temperature. So this is a standard electrode potential. So hopefully all of you are clear what is electrode potential and what is standard electrode potential, E naught, right? So and I am putting here note. For E naught, temperature is not should be constant, not necessarily necessarily 298 Kelvin. 298.15 Kelvin. Right? So make it a clear note that for E naught temperature should be constant, not necessarily 298 Kelvin, but if nothing is mentioned, nothing is mentioned, then it is 298.15 Kelvin, right? If nothing is mentioned, then it is 298.15 Kelvin. Okay. Well, so now it is clear to all of you that what is E and E naught. Now see how to represent E and E naught for any reaction. So in the above case, we have this half cell reaction Zn solid, and it will give you Zn2 plus 2 electron. So any reaction, I mean, if represented, you have to always read that reaction from left to right. This is the normal convention. So this is which type of reaction is this? This is a oxidation reaction. So you can write here E of what is converting to what? Zn is converting to Zn2 plus. So you have to write like this. So this is equal to, suppose that some x volt, right? So how to read this? You can say that the oxidation potential of zinc is x volt, right? And you should write like this. Similarly, under standard condition, this is E naught. So how to write this? E naught for Zn oblique Zn2 plus, this is equal to, let it be Y volt. Means you can say that E and E naught are not equal for any given electrode, right? E naught and E are not equal for any given electrode, right? Clear? And you know, we have two types of potential. E is of electrode potential is of two type, and you can say E oxidation and E reduction. E reduction, right? Or E naught, you can say, it is better. E naught oxidation and E naught reduction. For any given, see, for any given electrode, E naught oxidation is always equal to E naught reduction. Magnitude, right? This is always true for any given electrode. Means E naught of Zn2 plus E naught of Zn2 plus, this is oxidation potential, this is equal to the E naught of Zn2 plus oblique Zn, right? And this is always true. This is reduction and this is oxidation, right? So for any given electrode, the E naught oxidation and E naught reduction both are always equal. Magnitude wise, sign is opposite, right? Now see, what is the property of this E naught? What is the property of E naught and what is the application? So property and application of E naught, this is very important. And what parameters are present, what thermodynamic parameters are present in the calculation of E naught, right? So first I am taking what thermodynamic parameters. Thermodynamic parameters involve in the determination of E naught. So number one, enthalpy of sublimation, enthalpy of sublimation for solids, right? Enthalpy of sublimation for solids, enthalpy of vaporization for liquids, and for gases there is no enthalpy of sublimation or vaporization. For gases it is enthalpy of dissociation, but I am taking solid. On the basis of this you can visualize other things. Sublimation and then enthalpy, ionization enthalpy, delta H ionization. This is called ionization enthalpy, right? After that, third thermodynamic parameter involve the hydration enthalpy, hydration of ion. Hydration enthalpy, right? Delta H hydration. See, the IUPAC rule is this, that you have to write the process with the delta then H. Many times you will find the delta H, after that people are writing this process, but the IUPAC convention is this. So ionization enthalpy, hydration enthalpy, and ionization enthalpy for cations, and electron gain enthalpy for anions, right? So enthalpy of sublimation, enthalpy of ionization for cation, and delta electron gain enthalpy for anions, and hydration enthalpy. So this is the reason why E naught is different for different material, because copper and zinc has different enthalpy of sublimation, copper and zinc has different ionization enthalpy, and copper and zinc has different hydration enthalpy. So this is the reason why different electrodes have different what E naught values. And you know, once you talk about E naught, if you conclude anything in terms of E naught, means you are considering all these things or not, because these are the parameters involved in the determination of E naught. Means E naught apparently have all these terms, because you know on the basis of this you have to calculate what enthalpy, net positive, negative, negative, positive, whatsoever value, you will get delta H and delta S, then you have to calculate delta G. And all of you are knowing that this delta G is equal to minus W useful right, W useful. Now see this delta G is equal to W useful, and here in electrochemistry the useful work is electrical work, and electrical work is always useful work. So electrical work is equal to N into F into E. So we can write here minus N F into E, right? So this is equal to delta G. So this is very important formula for this chapter, and whole chapter is based on this formula only. See, you can use this formula for half cell, or on complete cell. Complete cell means any half reaction is given, then you can calculate delta G for that. And then when you are using on the half cell, then this will give you the electrode potential, and if you are applying on the complete cell, then this will give you the EMF, right? And under standard condition, delta G naught is equal to minus NFE naught. So these are the important formulas used in this chapter. So, and delta G you can calculate by using these parameters. Delta G is equal to delta G naught is equal to delta H naught minus T delta S naught. So this is equation 4. So what you have to do, see, this is delta H, this is delta H, this is delta H. So you have to make a Hess law and calculate the total delta H. Whatever the plus minus, whatever the value, you will get delta H. Of this, experimentally determine delta S at given temperature. You can find out the delta G naught, put here value and get the electrode potential. So this is the way how to calculate E naught for any electrode potential, right? Good. So now how to what are the properties of E naught, and meaning of E naught and its calculation. So E naught characteristic properties of E naught. So when I'm writing here, E naught means E naught oxidation and E naught reduction, both I am including here, right? So what is the characteristic property of E naught? So the characteristic properties of E naught see, the first characteristic property of E naught is intensive property. Intensive property. So what is the meaning? What is the feature of intensive property? That is, cannot directly directly add or subtract. Subtract. Subtract, right? So what we have to do, first we convert this into extensive property, then we can add or subtract. Delta G naught is extensive, this is extensive. So whenever you have two or more equations, half equation or complete equation, and it is asked, okay, to calculate E naught for any given reaction. So what you have to do, you have to convert this E naught into delta G naught by using this equation, and then you have to calculate, right? What is F here? Here F is the Faraday's constant. See, F is called Faraday's constant, which is equal to 6.023 into 10 to the power 23 into 1.6 into 10 power minus 19. Basically, Faraday's constant is the charge present over 1 mole of electron. So this is equal to 96500 coulombs, right? Per mole, coulombs per mole. Okay. So delta G naught is extensive. So suppose that if you have a question like this is very important question, very important question, and this is based on this concept only. See, suppose that it is given Fe3 plus electron gives Fe2 plus, and E naught is given X volt, and Fe2 plus 2 electron gives Fe. For this it is given E naught is equal to Y volt, right? Suppose that question is asked that what is Fe3 plus 3 electron gives Fe, what is E naught for this? E naught for this, right? See, this is example. So what will happen? Usually, see, this is equation 1 and this is equation 2. So from thermodynamics, we have this, tendency that, okay, this is equation 1, this is equation 2. On adding, we are getting this equation, this plus this gives this. So this E naught is equal to X plus Y volt, right? So this E naught, see, this is equation 3. So equation 3 is equal to the equation 1 plus equation 2 plus equation 2, right? So you can write E naught for equation 3 is equal to X plus Y volt, and you know your answer is incorrect, right? You cannot write like this directly. E naught you cannot add or subtract. See here, you cannot directly add or subtract. Okay, clear? Good. So what we have to do? From equation 1, calculate delta G naught. So delta G naught 1 is equal to minus N is the moles of electron here in this formula. So moles of electron here 1. So 1 into F into X volt, X volt, right? So this is delta G naught 1. Then calculate delta G naught 2. Delta G naught 2 is equal to minus 2 into X, and minus 2 into F into Y, and delta G naught 3 is equal to minus 3 into F into E naught, right? So now you can use delta G naught 3 is equal to delta G naught 3 is equal to delta G naught 1 plus delta G naught 2. So you can write minus 3 into F into E naught is equal to minus F into X minus 2 into F into Y, right? So this F cancel. So we can write here E naught is equal to X plus 2Y by 3 volt. So volt. This is the correct answer. This is the correct answer, right? So you cannot directly add or subtract what? E naught. You have to convert in terms of delta G naught and then, right? And you know, from this equation 3 you can say if E naught is positive and delta G naught is what? Negative. If E naught is positive, then delta G naught is negative, means reaction is spontaneous. If delta G naught is negative, then E naught is positive, then reaction is spontaneous, right? So delta G naught negative and E naught positive. This is the condition for spontaneity. Means cell reaction or half cell reaction. Half cell reaction is spontaneous. Is spontaneous, right? Cell reaction or half cell reaction is spontaneous. So this is the first property, and this is very useful property for this chapter, and you will find many questions based on this, right?